All right. If you don't recognize what I have up here, you may want to go back and make sure that you finish the lectures over stoichiometry, particularly those dealing with the change in energy that accompanies reactions. What I have here is I have the combustion reaction of, it looks like ethine. So I have some ethine reacting with oxygen, shielded carbon dioxide, water, and energy. The energy released or gained during a chemical reaction is referred to as the heat of reaction. Wow, my handwriting is starting off sloppy today. Now, when a reaction is carried out at a constant pressure, and most reactions are carried out at a constant pressure. Anytime you carry out a chemical reaction in a container that doesn't have a cork in it, it's carried out at a constant pressure. When a reaction is carried out at a constant pressure, the heat of reaction may be referred to as the change in enthalpy. Enthalpy, the change in enthalpy, and that's spelled correctly and pronounced correctly, which is a rarity for me, I know. Don't confuse enthalpy with entropy, which is something else you may have heard about somewhere, not in this class. Change in enthalpy, however, is the heat of reaction at a constant temperature. And we like to give it its own special symbol. We like to use the symbol delta, and then we give it the capital letter H to represent it, after the chemist who did a lot of work with it, known as Hess. When we represent a heat of reaction as a change in enthalpy, we can rewrite that chemical reaction. So I'm going to rewrite that reaction we have up here. So I've got 2C2H2 gas plus 5 oxygen gas yields 4 CO2 gas, of course, plus 2 waters gas. I should have put gas up there. Gas. Then I would write semicolon delta H negative 2512 kilojoules. Just as a quick review, remember, whenever energy is produced as a product in a chemical reaction, sign is negative. When the sign of the change in enthalpy is negative, and when energy is a product, we refer to the reaction as a exothermic reaction. Again, this should be review, but for an exothermic reaction, everybody write down Frosty the Snowman. I hope everybody wrote down Frosty the Snowman. Energy is released. It can be written as a product or can be written as a negative value. And we just looked at an exothermic reaction. So the opposite of an exothermic reaction is, of course, all right, let's talk about endothermic reactions, which are the opposite of exothermic reactions. In endothermic reactions, energy is added to the system in other words, energy functions as a reactant and can be written on the reactant side, or if we want to write it in terms of change in enthalpy, or if we're going to write it in terms of change in enthalpy, a positive number. If we're going to write an endothermic reaction in terms of change of enthalpy, we'd write the reaction. But whenever we do changes in enthalpy, and that's a solid, by the way, that's an S in case you can't read my chicken scratch there. We'd write our reaction. We'd write a semicolon. And even though energy is a reactant in this equation, we still write that delta H symbol at the end, but we make the number positive instead of negative, since it's an endothermic. So that's an endothermic reaction. Now, hopefully, everybody's up to speed and you don't need Rudolph to guide your sleigh. So why don't you write down Rudolph for me? Everybody write down Rudolph. And now for something new. Now we're getting to something new that you probably haven't seen in lecture before. Most of what you're doing in today's lab is going to be based on two things. The first of these is the law of conservation of energy. And the law of conservation of energy, as you probably have heard before, says energy cannot be created or destroyed. But it has some more interesting implications. When we think about the law of conservation of energy, we divide the universe, everything in existence, into two parts. The system, which is what we study, plus the surroundings. And since energy can't be created or destroyed, that means that the energy of the universe is constant, which is another way of saying the change, remember, triangles in chemistry mean change, the change in the energy of the universe is equal to 0. The energy never changes its energy. And since the energy of the universe is equal to the energy of the system plus the energy of the surroundings, and remember the system is what we study, our chemical reaction that we're interested in, and the surrounding is everything else in existence. That means that the change in energy of the system plus the change in energy of our surroundings also has to be zero. There's a startling implication to this that may be slowly occurring to some of you. That means that if our system loses energy, then the surrounding gains energy. Because that energy can't be created or destroyed. It has to go someplace. But it also may occur to you that the opposite's true. If the system gains energy, since it can't create that energy from thin air, it means that the surroundings must lose energy. So, because the energy of the universe is constant, the change in the energy of the system plus the change in the energy of the surroundings is equal to zero. And if the system loses energy, then the surroundings gain it. We see this all the time. If you hold a hot cup of coffee in your hand, what happens? Your hand gets warm, right? Your hand is the surroundings. Your surroundings, your hand, is gaining energy from that coffee. What happens to that coffee over time? It gets cooler because it's transferring energy from itself, the system, the coffee cup, to the surroundings, your hand. One gains, somebody else loses. I try to explain this to my wife all the time. My wife constantly complains that she can feel my cold feet in bed. And I have to constantly tell her that she's not really feeling my cold feet. That she's really feeling the heat leaving her feet. Because my feet are the surroundings and her feet are the system. Somehow she finds no comfort in this fact. All right, what we want to do now is we now want to add our first mathematical formula. And this is a really neat little formula that has to do with specific heat. Now, what is specific heat? Specific heat is the amount of energy it takes to raise the temperature of 1 gram of a substance by 1 degree Celsius. Remember that a degree Celsius is the same size and magnitude of a Kelvin. Now, if you remember how large a gram is about the mass of a paperclip, right? So we're talking a very small amount of mass, and we're only raising it by 1 degree. So the specific heat of an object is usually a very, very small amount. Water has a specific heat of 4.184 joules per gram per Celsius, or if you like, 4.184 joules per gram per degree Celsius. Now, the specific heat of water is a little unique. Well, let's talk about this real quickly. The specific heat of water would be 4.184 joules per gram per Kelvin. That means that if I have 1 gram of water and I want to raise the temperature by 1 Kelvin, I need to have 4 joules of energy in order to accomplish that task. The specific heat of water is actually used to define a unit of energy, and the unit of energy the specific heat of water is used to define is a calorie. 1 calorie, lowercase c, is defined as the energy needed to raise 1 gram of water by 1 degree Celsius. Now, different substances have different specific heats. So water has a specific heat of 4.184 joules, or we could say that water has a specific heat of 1 calorie per gram per degree Celsius. This value will come in very, very important later on as we begin to look at the lab. But how would we use specific heat mathematically? Let's take a look at our specific heat formula. Our specific heat formula would be, crap, I forget it. Or maybe I should use another word for crap. The heat or energy needed to raise a given mass of water in grams is equal to the mass of the water times the specific heat of the substance for water, it's 4.184 joules per gram per Kelvin, times the temperature change. Delta T is the temperature change, and the temperature change is always the temperature final minus the temperature initial. I cannot stress enough how important it is that you remember that when you're doing temperature change, it's always final minus initial. If you don't do finest minus initial, you'll get the positive and negatives for your endo and exothermic processes wrong. Remember, to boil water is an endothermic process requiring heat. But when water cools, it gives off heat, and therefore it's an exothermic process. So we need to keep those thoughts in mind. So let's work a simple problem with this one. Jack wants to raise the temperature of 25.3 grams of water from 5.7 degrees Celsius to 38.9 degrees Celsius. How many joules of heat will this take? So Jack wants to raise the temperature of 25.3 grams of water from 5.7 degrees Celsius to 3.89 degrees Celsius. How many joules of water will this take? Well, we know our formula. Energy equals mass times specific heat times and change in temperature. They told us that we had a mass of 25.3 grams. I've told you that the specific heat of water is 4.184 joules per gram per degree Celsius. They told us that we have a final temperature that we're heating to of 38.9. And we have an initial temperature of 5.7. So now we've got everything plugged in. Mass, our specific heat, our change in temperature. So now we're going to plug and chug away here. 25.3 times 4.184 times the quantity, 38.9 minus 5.7, close parentheses, and that gives me 3,500 joules. Well, actually, it's going to be one more sig fig there, isn't it? 1. Just so you know, the calculator lie is 3,514.39264, but we've got 3 sig figs there, 3 there. When you subtract 5.7 from 3.8, you still have 3 sig figs left, so we're going to have 3 sig figs in our answer. So that's why I wrote it that way. But your calculator will actually give you 3,514 point however many joules. Alrighty. That's it. Chemistry's easy. Life is hard for that one. Let's kick this party up a notch. Let's roll specific heat in with the concept of conservation of energy. Write down TARDIS. The reason I'm telling you to write down TARDIS is because I can't think of anything else for you to write down, and I've got about 3 in my office. TARDIS. All right. Here's a problem that's pretty easy and pretty straightforward and uses both the law of conservation of energy and uses specific heat. Classic scenario. I've got a cup of hot water here that contains 10 grams of water at 80 degrees Celsius. And I have a cup of cold water here that contains 25 grams of water at 15 degrees Celsius. If I mix the two together, what will my temperature be? How can we figure that out? Well, let's think about what's going to occur when we're going to mix these two things. Our hot water is going to cool, and our cold water is going to warm, right? Our cold water will get warmer when we pour the hot water in it, and our hot water will get colder when we mix it with the cold water. Since it involves a change in temperature, is going to involve my specific heat formula. For my hot water, I'd have the Q of the hot water, or the heat of the hot water, would equal the mass of my hot water times the specific heat of water times the temperature change that my hot water would undergo. In this scenario, we know what all those things are. So, the Q of my hot water would equal a mass of 10 grams times the specific heat of water, 4.184, times the temperature change of the hot water. And we'll just leave temperature change like it is for the moment. Now, my cold water down here, likewise, the heat flow from my cold water, due to its temperature change, is going to equal the mass of my cold water times the specific heat of water times the temperature change of my cold water. So the heat flow of my cold water would equal 25 grams, 25 grams of water times the specific heat of water times the temperature change of my cold water. So now I've got two equations. Each equation is missing both a heat flow and the information about the temperature change. How can we come up with a way of resolving this? That's where the law of conservation of energy comes in. Remember, the law of conservation of energy says that the change in the energy of the universe, or the change in the heat flow of the universe, is equal to 0. That means that any heat lost by my hot water as it cools has to be gained by my cold water. Conversely, any heat gained by my cold water has to be lost by this hot water. And since exothermic processes, such as the hot water cooling, have the opposite sign of endothermic processes, the cold water warming, we can safely say, based on the law of conservation of mass, that since the change in the energy of the universe, the change in the heat flow of the universe, is equal to 0, and our universe consists of two parts. It consists of our hot water and our cold water. Then the heat flow of our hot water plus the heat flow of our cold water has to be equal to 0. That means, by substitution, that 10 grams of water times 4.184 joules per gram per Kelvin times the change in temperature of hot water plus the heat flow of my cold water is going to be equal to 0, where my heat flow my cold water is 25 grams times 4.184 joules per gram Kelvin times my change in temperature. So now we have an equation where we only have two variables now. The change in the temperature of the hot water and the change in the temperature of the cold water. With a little bit of algebra, we can reduce this to one variable. All right, I haven't planned my space well. How can I do this? All right. Ooh, that kind of works. So here's what I can do. I have 0 is equal to my 10 grams of hot water Sometimes this stylus lags a little bit for whatever reason. the temperature change of my hot water there is always going to be my temperature final minus my initial temperature. And my initial temperature of my hot water, if you'll remember, was 80 degrees Celsius. And I got that from my picture down there, right? I circled it. If you look where my pen produced a black circle down there. Plus the 25 grams for my cold water times that 4.184 times, shoot, I always write a little bit big, times the temperature change of my cold water. Now, my cold water and my hot water, because they've been mixed together, they eventually become one big pot of water with the same final temperature. So the final temperature of my cold water is the exact same as the final temperature of my hot water. But their initial temperatures will be different. My cold water, remember, started out at that 15 degrees Celsius down there. See, I circled it again. So now we have something that's just a really ugly math problem now. So now it just becomes a matter of doing the algebra. 41.84 joules per gram Kelvin. Actually, my grams have now gone away, so it's just joules per Kelvin, or joules per degree Celsius. Let's keep it simple. And 25 times 4.184. 25 times 4.184. $104.6, right? I multiplied those two together. Joules per degree Celsius. And we can comfortably say that it's equal to 0 at this point. What I'm going to do is I'm going to move one of my equations over to the other side of the side. And when I do that, it's going to become negative. So I'm moving this over to the other side. So I'm subtracting it. So I've got a negative 41.84 joules degrees Celsius times TF minus 80 degrees Celsius equals 104.6 joules per degree Celsius times TF minus 15 degrees Celsius. Now I'm going to distribute, and that means I'm going to multiply my 41 times my TF and my 41 times my 80. So that gives me a negative 41.84 TF plus 41.84 times 80, 3,000.2 joules equals, and now I'm going to distribute over here again, right? I'm going to multiply my 104.6 times my TF and my 104.6 times my 15. And notice because I'm multiplying by a negative over here, my negative times a negative is a positive. That's why that's positive, but that remains negative. So on my other side of my equation, I have 104.6 joules degrees Celsius TF times my TF. And now I'm multiplying by 15. 104.6 times 15 equals 1,569 joules. Well, I now have two numbers with TFs and two without them, so I'm going to combine them on the like sides here. So 3,472.2 joules plus 1,569 joules. The sign changed because I moved it onto the other side, equals 104.6 TF plus 41.84. Again, I switched sides, so it changed. I know. This is a lot of algebra. Plus 3,347.2. 4,962 joules equals 41.84. That was really messy. Just a second. Let me see if I can clean that up for you guys. Or maybe not. There we go. I now want to get my TF by itself. So I'm going to divide both sides by 146. Sorry for the silence there. I was just double checking my calculator work. And what did I do wrong? I gained a decimal point somewhere. Oh, that should have a decimal point right there. That's it. I dropped my decimal. So let's try that again, shall we? 4,916.2 divided by 146.44. There we go. That's much better. Gives us 33.6 degrees Celsius as the final temperature of our water mixture. So that's a simple but long way, took us close to 15 minutes to work that problem, that we can use the law of conservation maths and specific heat. If you think about it, what we did is really simple. It just took a lot of time to churn through that algebra. But this process of saying that the related heat flows are equal to zero, like we did, that initial statement of adding up different heat flows to equal zero, that is at the heart of the science called calorimetry. Now, calorimetry is the study of heat flows. And I could go on all day about it. Matter of fact, I sense I'm going a little bit off track and a little bit farther than I need to do. So if you haven't already, stop and read your lab. Not just the pre-lab, but the entire lab set of instructions there, pardon me. And then come back for part 2 of this lecture, where we'll walk through the math, just specifically focusing on the math that you're going to have to do in today's lab. Before we do that, why don't you write down the wiggles? Everybody write down wiggles.